All right, here are our answers to projectile motion 2. While filming a movie, a bus that's on fire drives to the edge of a cliff with a velocity of 25 meters per second, and the driver jumps out the window. Exactly 2 seconds after it leaves the cliff, the bus explodes in a spectacular fireball. Okay, so how far horizontally from the cliff does it explode? This means right now we're just looking at our x stuff. Now, in the x direction, we automatically know that the acceleration is going to be 0. So it doesn't matter what any of that other stuff says, that's going to be 0. Now, when we read this, it drives off the cliff with a velocity of 25 meters per second. What's really important here is that we know that this is the initial velocity in the x direction, and 2 seconds later, the time is going to be 2 seconds, it explodes. So I know that the initial velocity in the x direction is 25 meters per second, and I know that the time is 2 seconds, and the acceleration is 0, and I want to know how far my object goes. So looking at all of this stuff, if I want delta x, we're going to use the third equation. Delta x is v initial times time plus 1/2 acceleration times time squared. If we plug all the things in that we have, delta x is equal to 25 times 2 plus 1/2 times 0 times time squared, so times 2 squared. But since the acceleration is 0, that whole term goes away. Since I'm moving with constant velocity, my displacement is just going to be the velocity, 25 meters per second, times the time, 2 seconds, or my delta x is 50 meters. The horizontal direction is great because in the horizontal direction, constant velocity, no acceleration, super easy equations. But in the vertical direction, if I drive off the cliff and my velocity is in the x direction, in the y direction, in the vertical direction, my initial velocity in the y direction is going to be equal to 0. And in the y direction, my acceleration is 10 meters per second squared down, and my time is still 2 seconds, and what I want is delta y. Now, it's the same given information, so we're going to use the same equation. We're going to write it for delta y. So delta y is equal to v initial times time plus 1/2 acceleration times time squared. So delta y is equal to 0 times 2 seconds plus 1/2 times 10. We don't have to do a negative sign because everything's down, times 2 squared. So my delta y ends up being 20 meters, and it's 20 meters down because we fall down below the cliff. So if we were going to draw this situation, the car would start here and would fall off the cliff this way, and then the car would explode. So it starts off with that speed of 25 meters per second, and that's all in the x direction. Nothing's in the y direction. It keeps that speed of 25 meters per second in the x direction till it explodes. But in the y direction, speed in the y starts off at 0, and it grows and it grows and it grows. Number 2, car drives off of the edge of a cliff that is 45 meters high, that's y direction stuff, and it lands 72 meters away, that's x direction stuff, from the base of the cliff. How fast was the car going before it left the cliff? So here, everything's all in the same spot. Now, in this problem, we have horizontal stuff happening and we have vertical stuff happening. Before we even write anything down from the problem, the acceleration in the x direction is 0. The acceleration in the y direction, the vertical direction, is 10 meters per second squared down before we do anything else. Now, because we're driving off the edge of the cliff, the velocity is going to be in this direction. So, in the y direction, because we're going off the cliff horizontally. All the initial velocity is in the x. So the initial velocity in the y direction is 0 meters per second. And my delta y, since it's a 45-meter tall cliff, I start off at the top of the cliff and I end at the bottom of the cliff. That makes my delta y, right color here, 45 meters down. So that's everything I know in the y direction. Moving on to the x direction, I don't know my initial velocity. That's what I'm looking for. But I do know my displacement in the x direction is 72 meters. And since we have constant velocity and my acceleration 0, the equation I would use here is velocity is displacement over time. This is what we use when we have no acceleration. Only problem is I don't have time over here in the x direction. What I can do is find the time in the y direction, and then, since it's happening simultaneously at the same time, I can move that over into the x direction. So I want to solve for time here. So I've got delta y is equal to v0t, v initial times time, plus 1/2 acceleration times time squared. Went off a little bit. 1/2 time acceleration times time squared. So 45 is equal to 0 times t plus 1/2 times 10 times t squared. So in this case, I'm not going to do anything with negative signs because everything's down in the y direction. This 0 term goes away, and I get 45 is equal to 5t squared. Divide both sides by 5, and I get 9 is equal to t squared. So what that tells me after I square root both sides is that t is equal to 3 seconds. So I can take that over here and say, all right, well, the velocity in the x direction is 72 meters divided by 3 seconds. That makes the velocity in the x direction 24 meters per second. That's how we're going to solve problems like this. We're going to split things up into the x direction and the y direction. We're going to find time in one of those directions. We're going to go back and use it in the other one. So, number 3. We have x stuff and we have y stuff. A car rolls off the edge of a table with a speed of 5 meters per second. That is the velocity in the x direction, 5 meters per second. Since it's rolling off that table, it tells me the initial velocity in the y direction is 0. The table is 0.8 meters tall. That's y direction stuff. Again, I love drawing a little sketch for this. We're going off at 5 meters per second, and we're falling down 0.8 meters. So my delta y is 0.8 meters down. And I want to know how far away from the table the toy car will land. That is an x direction question. How far away from the table will it land? So I want to know the delta x. I also know that the acceleration in the x direction is 0 because we're a projectile and there's no acceleration in the x direction, and that the acceleration in the y direction is 10 meters per second squared down. So what we're going to do is find the time in the y direction, and we're going to use it over here in the x direction because my delta x is velocity times time. So I've got delta y is equal to v initial t plus 1/2 at squared. So delta y, 0.8 is equal to 0t plus 1/2 times 10 t squared. The 0 goes away because when you multiply by 0, things go away. And I get 0.8 is equal to 5t squared. We divide both sides by 5. So when we do that, we get 0.16 is equal to t squared. So my time comes out to be 0.4 seconds when you square root both sides. So my delta x is going to be the velocity, 5 meters per second, times my time, 0.4 seconds. And so my delta x comes out to be 2 meters. That's how far away from the edge of the table our object lands. Number 4, while standing on top of a building, a group of students launch a water balloon horizontally with an initial velocity of 15 meters per second. So again, to draw a picture to help us a little bit, we're on top of this building. We're shooting the water balloon with a velocity of 15 meters per second in that direction. So we're going to have X stuff happening and we're going to have Y stuff happening. That 15 meters per second is the initial velocity in the X direction, and the initial velocity in the Y direction is going to be 0 because that is all horizontal. The balloon is going to land 33 meters away. That is our delta X, 33 meters. And I want to know what's the height of the building. That's the delta Y. I want to know that. Now, for both of these, we know the acceleration. The acceleration in the X is 0, and the acceleration in the Y direction is 10 meters per second squared down. Now, in order to get the delta Y, the equation we've been using is delta Y is equal to V initial t plus 1/2 AT squared. What I need is time. I don't have that in the Y direction, so I'm going to find time in the X direction. So we can do this a couple different ways. We'll go the long way. Delta X is equal to V initial times time plus 1/2 AT squared. So delta X, 33, is equal to 15t plus 1/2 times 0 times t squared. Well, that 0 part goes away, so I don't even have to worry about this chunk of the equation anymore. We'll divide both sides by 15, goes away over here, and my time comes out to be 33 over 15. Which is 2.2 seconds. So now we can use that time in the Y direction. Delta Y is 0 times 2.2 plus 1/2 times 10 times 2.2 squared. So we can put all that into our calculator. And our delta Y comes out to be 24.2 meters. So the height of the table is 24.2 meters. This one was a little bit different in that we found the time in the X direction and then put it in the Y direction. All right, for number 5, we have pirates on the deck of their ship. And it's 7.2 meters above the surface of the water. Get rid of all that. We're 7.2 meters above the surface of the water. That's delta Y. The cannonball lands 74.4 meters away. That's delta X. And I want to know the velocity of the cannon when it left. That is the X velocity when the object left. So let's go through this. We have X stuff. We have Y stuff. We know always that the acceleration in the X direction is 0. And the acceleration in the Y direction is 10 meters per second squared down. We're going to shoot this thing horizontally, so the initial velocity in the Y direction is 0, and it tells us that we land 7.2 meters above the surface. We land 7.2 meters below where we shot. So we're 7.2 meters below where we shot. And in the X direction, my displacement is 74.4 meters. That's how far away we land. So if I want the velocity when the acceleration is 0 in the X direction, that's delta X over time. That's how we find velocity without acceleration. What I need is time. I have to get that from the Y direction. So the equation that has all those things in it, delta Y is equal to V0t plus 1/2 AT squared. Plugging in our numbers, 7.2 is equal to 0 times time plus 1/2 times 10 times time squared. So the 0 times time part goes away, and I get 7.2 is equal to 5t squared. And so let me move over a little bit. We've got 7.2 is equal to 5t squared. We'll divide both sides by 5. And then I have 1.44 is equal to t squared. We'll square root both sides of that, and the time comes out to be 1.2 seconds. So we're going to take, we're going to put that in over here. So we know that our velocity is 74.4 meters divided by 1.2 seconds. So the velocity in the x direction comes out to be 62 meters per second. I hope we're starting to see a little bit of a pattern here. Let's do it again. Same kind of thing. Our height is 1.25 meters. Our initial velocity is 200 meters per second, and I want to know how far away. So in the x direction, the acceleration is 0. The initial velocity is 200 meters per second, and we want to know the delta x. But in order to find that, we need time, because delta x is velocity times time plus 1/2 acceleration times time squared. The acceleration is 0, so that whole part goes away. Delta x is initial velocity, 200 meters per second, times the time, but I don't have that yet. So I need to go over to the y direction. Well, I know in the y direction, the acceleration is 10 meters per second squared down. I know that my height is 1.25 meters down, again, because we're firing it this way, and it's going to fall down in the y direction. My initial velocity in the y direction is 0 because we're firing it horizontally, and we want the time. So the equation that has all of that in there is delta y is equal to v initial times time plus 1/2 acceleration times time squared. So 1.25 is equal to v initial 0 times time plus 1/2 times 10 times time squared. This term goes away because we're multiplying by 0. I get 1.25 is equal to 5t squared. So we're going to take and divide both sides by 5. 5 goes away. And I've got now 0.25 is equal to t squared. So we're going to square root both sides. So 0.5 is equal to our time. 0.5 seconds is our time. We're going to plug that in over here. And our delta x is equal to 200 meters per second times 0.5 seconds. Our delta x comes out to be 100 meters.